Okay, yesterday I mentioned shape charges, and I said I'd bring my shape charge piece in. This is a shape charge piece of copper, and it basically is just a saucer-shaped piece, and it's got little places where you would put a little bit of explosive in each one of those, and when you set it off, the saucer will invert. Okay, you'll have a downward force on the outside rim of this thing, and the thing will invert, and all the copper will be squeezed into the center underneath. And as it does that, you'll have adiabatic heating, and the copper will melt, and you'll shoot out a jet of liquid copper out of there. And that jet of liquid copper will penetrate a piece of steel to about whatever the length of the piece of copper is, and it will do it in microseconds. Okay, so this is another shape charge design. So this is your terrorism lesson for today. If you just took a piece of copper, a round copper bar, and you milled a 90-degree slot in it, okay, I guess I could do a little better job of. So you're just going to mill a 90-degree slot in it, and then you put your stick of dynamite on here. Then when the dynamite explodes, this unfolds back on itself, and you will get a shape charge. And in fact, that is exactly what they use when they want to tear down buildings, demolish buildings. They'll take a little bar of copper, they'll put it right up against the I-beam, and they'll tape a stick of dynamite to it, and when they set that off, the dynamite will go off. The stick of dynamite here will go off. The copper will fold back on itself. Adiabatic heating from all the energy. Molten copper will just slice right through the beam. Okay, so that's how they demolish buildings. Okay, so I know something about some of this stuff mostly because I used to be on the Army's advisory board for their ballistics folks, but also because of my World Trade Center paper. The conspiracy theorists say it was a thermite reaction that brought down the World Trade Center, and I said that's ridiculous. No one would use a thermite reaction to bring down the World Trade Center. It wouldn't work. And it turns out National Geographic ran a special and spent $360,000, and most of it went to actually testing the theory of whether a thermite reaction, which is a reaction between iron oxide and aluminum powder, which will melt steel. That's the way we weld railroad rails together, is with thermite reactions. We've been doing it for 100 years. But they actually set it up at the Explosions Research Center in Sirocco, New Mexico, which is part of the University or New Mexico Institute of Technology, I guess. They have a big mountain there, and they have an explosives research center, and they'll blow up anything for a fee. And they actually ran the test for National Geographic, had an I-beam column, packed it around with thermite reaction, set off the thermite, and all it did was make a bunch of heat. Didn't cut the beam in two, just like I said. Okay. But anyway, there's a National Geographic special on the World Trade Center collapse that actually shows me holding that little piece of copper as I was explaining to them. This is how you would set it off. And then they went to a dormitory in Louisiana where some demolition guys were blowing up this dormitory because it was an old dormitory, and they actually had these types of shape charges, and they duct taped them to the building beams and stuff. And anyway, well, they told the demolition experts the conspiracy theorist hypotheses about how the World Trade Center came down. Those guys just laughed on the screen. They said that's ridiculous. Okay, I said it was ridiculous too. But anyway, so we were talking yesterday about these quotes, and I was thinking a little bit more. One of you said that you didn't believe the quotes, and this is for new materials. It's not for older materials that are more mature, that have gotten into the reduction of cost processing stage. This is some new material with fantastic properties, and it's always not quite as good as the developer thinks. But I think the criticism yesterday was correct, and we'll actually, when we get to steel, show that steel technology is now in the reduction in cost reduction through processing stage, and it's not a new material, okay? And so Sprague's law doesn't apply to an old, mature product. Yeah.
When you're looking at new materials, they're always going to have this kind of thing. They're flashy. Everyone's trying to promote them. As someone who's seen a bunch of this type of thing, how do you know if the material is worth it? You said go to the science, but like a lot of them have scientific, like.
Yeah, but the people who are selling it are not really being honest about the science. They usually improved one property, and when you're actually designing a system, you need a suite of properties. You need strength, you might need corrosion resistance, okay? Originally, steel was a wonderful material, had plenty of strength and ductility, but it still today has lousy corrosion resistance. Okay, that's one of the Achilles heels of steel is corrosion resistance, even today. Well, someone came along with stainless steel, and everybody thought that was wonderful. And we'll talk about the fact that stainless steel is not as wonderful as everybody thinks. It's stainless, not stain-free. Okay, so usually, if you start thinking about the various properties, sort of like my example of the electrically conductive polymers. They said, oh, well, they've got a specific electrical conductivity. Yeah, but that's not the figure of merit for the design, okay? And so people will talk about composites and fancy composites. I remember Professor Gutowski in mechanical engineering, I guess it's over 25 years ago now, when the LFM program first started, he had a group of students go to Boeing working on advanced composites. This was supposed to be for the 777. The 777 was supposed to be 80% composites. Well, they canned that after a couple of years, and they made it mostly aluminum, just like the previous aircraft. The 787 finally did, 20 years later, make it to a fair amount of composites. But there's lots of problems. But I remember Professor Gutowski came back. He works in environmental things now, but he's working in advanced composites. And he came back and he says, I've been working on the wrong thing. Okay, he says, I've been trying to make better composites. What we need are cheaper composites, okay, which is sort of Jim Williams' corollary. People have fantastic composites with tremendous strength, but you can't afford them. Okay, so whether it's cost or whether it's properties, these things often have an Achilles heel. And you kind of need to go to someone who's going to be an honest broker, who's going to say, who knows the area, okay? I knew superconductivity, and I knew that we weren't going to, and it wasn't just me. Like I said, there were 5 people in the department who had worked in superconductivity, and the only one who joined the bandwagon, aside from all the other people who knew nothing about superconductivity, was the untenured one. The 4 tenured professors would not touch this material because we knew what the problems were, okay? Other people who didn't know what the problems were, oh, they were cheerleading. They were saying, oh, this, you know, we're going to be riding on magnetically levitated trains. Well, that was 25 years ago, okay? And we're still not riding on magnetically levitated trains. That's not to say that the high temperature superconductors haven't found a niche. Anybody know what their niche is? The generators for wind turbines. Turns out you really need lightweight up there. And those generator shafts are steel shafts that can be 20 inches in diameter in one of these really big wind turbines. And you need lightweight. Well, it turns out you want something that's better, has better electrical conductivity than just straight copper. Copper's pretty heavy. Silver is pretty heavy too, and these superconductors are actually silver wires. But if you cool them to liquid nitrogen temperatures, you will get some superconductivity in this silver matrix. And I remember 20 years ago, I was at a National Materials Advisory Board meeting, and they were talking about, well, we should have some talks about certain things, new materials and This wasn't too long after, 5 or 6 years after the high temperature superconductors came along, and someone says, "Oh, we should have a talk from somebody about high temperature superconductors." I said, "You mean cold silver?" And there was only one person in the room who understood what I meant. If you cool copper to liquid nitrogen temperatures, it will have about 5 times lower resistivity because it's cold. If you go down to liquid helium temperatures, it'll have about 20 times lower resistivity. It's not a superconductor, okay? And silver is even better than copper, we said, as an electrical conductor. Well, at the break, Ed Van Ruth, who works at the Naval Research Lab and has worked there on superconductivity all his career, comes up to me and says, "Tom, it's not just cold silver." He didn't say it wasn't cold silver, okay? He says it's 20% better than cold silver. Okay, I mean, oh, wow. I mean, we've spent billions of dollars studying high temperature superconductors, and we've got something that's better, 20% better than cold silver. Okay, but it has found a niche, and its niche, it has actually 2 niches. They've tried to put a transmission line in the center of New York City for a DC transmission line. It has to be DC because superconductors don't work well with AC. That's another story. But they built a DC transmission line. There's not a lot of room underground in New York City. There's all kinds of wires and pipes and everything else. And things are very crowded in Manhattan. And so they actually put in half a mile or something as a trial. And that was a number of years ago, but I don't know that they've ever done anything beyond that trial. But all the technology that had to go with that was horrendous. And there are applications for looking for submarines from space, okay, superconducting quantum interference devices. But, most of the great promises of high temperature superconductors have not held up. And it's because of some of the critical parameters. There's high temperature. There's 3 parameters. Actually, it's the first figure in my doctoral thesis. There's high temperature, there's high magnetic field, and there's high critical current density. Okay, if you go to too high current density, it loses its superconductivity. And I have this little phase space with 3 axes with each of these 3 things, and saying this is where you have superconductivity in this little octant of space. And the thing is, they had improved one property, temperature. And they actually had, along with that, gotten a high magnetic field, but they hadn't improved critical current density, and they still haven't today, 25 years later. Okay? And people were reporting all kinds of wonderful critical current densities parallel with the magnetic field. And all of us, I did my thesis over the magnet lab. Anybody who tried to publish a paper measuring the critical current for a magnet with the conductor parallel with the magnetic field, you wouldn't have gotten your paper accepted, okay? Because anybody knows you got J cross B forces which will destroy the critical current if you have your conductor perpendicular, and that's how you design a magnet. You can't design a magnet with the current parallel. It's the J cross B, the vectors, the vector products. The current has to be perpendicular to the self-magnetic field. That's physics, okay? That's, what's his name? Maxwell's equations, okay? We're going back to Maxwell's equations. But I'm sitting there reading Science magazine, and people have got wonderful critical currents. I had the highest critical current in the world for my thesis, okay? And people were publishing things that were 2 orders of magnitude above what I had, except they were parallel with the magnetic field, which means it was garbage, okay? But if you didn't know anything about superconductivity, and the people who were publishing this, the people who were reviewing the papers, they didn't know what they were talking about, okay? They might as well have gotten a high school student to do this, okay? And so one of the problems when there's lots of money, you bring out all the people who don't know what they're doing, okay? Because everybody will take the money, right? Does that answer the question? I have strong opinions about some of these things, and I'll tell them to you later. Okay. So people oversell new materials, And actually, new materials are actually very useful, but they're not quite as wonderful as people say. And it takes time to develop them. Okay, we're talking about cost still, and now we're going to talk about speed versus cost. And it turns out lightweight is more valuable the faster an object moves. And so the value, I said that for an automobile it's $2 a pound, or for an aircraft it's $200 a pound, weight saved. But if you're talking a disc on the engine, it might be not $200 a pound, it might be $2,000 a pound, depending on where you save it. So part of your criticism yesterday was when you make a blanket statement, the blanket statement doesn't always apply, right? It's too general. Well, this is one of the places where the blanket statement of $2 a pound for automobiles and $200 for aircraft doesn't apply. You can actually spend more for the material if it's in a critical application. And one of these is called a bladed disc or a blisk. And you'd love to be able to take the turbine disc, which right now has this complex geometry to join the turbine blade to the disc, and you have this heavy structure right in here. If you could weld these things together or cast them together, you could reduce a lot of weight in this thing. And it turns out that's exactly what has been done in some cases. I'll tell you the commercial case in a second. But here I've got circling the areas where we've saved weight on this blisk. The only commercial blisk that I know of actually happens to be on the Detroit Diesel Allison, now Rolls-Royce M250 engine, which they've made something like 10,000 of these engines. They go in helicopters and other things. And they actually cast the blades to the alloy, to the super alloy. It's all cast as one unit. Like I said, they've made 10,000 of these things, and it's a small turbine engine for helicopters and small planes, but not for great big commercial planes. People can't cast with the quality they need in the big disc. But that is one application. People are trying welding. The Air Force has spent tens, if not hundreds of millions of dollars trying to figure out how to weld blades to disc, because there's tremendous value. In fact, if you go to a typical aircraft, the weight savings multiply. If I can save 20 pounds on a disc, and I got multiple discs in the aircraft, I've got multiple engines in many of the aircraft. Saving 20 pounds on a disc would mean 200 pounds on the engines and 2,000 pounds on the airframe. That's not a big deal for a commercial aircraft, but for the Air Force, 2,000 pounds either means 2,000 pounds more fuel and extended range, or 2,000 pounds more ordnance and more bang for the buck, so to speak. Okay. It is literally bang for the buck. Okay. Okay, sprung weight is more important in automobiles. Here we have a disc brake and a drum brake, just nice color pictures off the internet. At one time, back in the mid-'80s, some people had developed a technique to cast aluminum silicon carbide metal matrix composites. Reagan had started Star Wars, and people thought, oh, this is inexpensive. We've lowered the cost of this composite material. And one of the things they wanted to do, and several of the automotive companies tried it, they made the caliper housing, caliper assembly, which has the little hydraulic pistons in here that squeeze against the disc pad. Here you have the little pistons. Actually, I have the piston right here, which pushes the drums up against the outer housing. Anyway, they wanted to make this out of aluminum silicon carbide metal matrix composite. It's cast iron right now. It's heavy. It's on the axle, which is bouncing up and down. If you can reduce the weight on the axle, you'll get better maneuverability and ride handling and whatnot. Anybody know what the automotive companies call the whole general area of handling and noise and stuff like that? NVH, noise, vibration, and harshness. Okay? And so the sprung part, what's on the axle, is a large contributor to noise, vibration, and harshness. And so if you're going to buy a Cadillac that's nice and quiet running and stuff, you want to have less mass on the axles. Anyway, they did, and everything was fine, except if you put the brakes on hard 2 or 3 times, this would start to overheat. Aluminum is a low temperature metal. It will creep at elevated temperatures, and all of a sudden the dimensions of this thing change, and when you apply the brakes, you have no force, okay, because the thing just sprung open, okay? So that didn't work. That was 25 years ago, but I've heard, I haven't looked at it, but I've heard that they have solved the problem probably with design and cooling and stuff of these things so you don't get brake fade, okay? So you'll pay more. The point is you'll pay more than $2 a pound if you're on the sprung weight, okay? So this $2 a pound is a general rule. It's not specific to everything. Another example from the aerospace industry is the X-33 space plane. This thing I've handed around. I won't hand it around again unless you really want it. But this came off one of the 2 liquid hydrogen tanks. The X-33 space plane was a project in the early 90s, $1.3 billion project, to build a prototype to replace the space shuttle. NASA knew the space shuttles, they had 5 of them, they weren't going to last forever, and they weren't economical like they were supposed to be. That was their purpose in the early 70s. And most people think the space shuttle was a civilian project. No, okay? Let's not have fantasy here. It turns out it was sold to the public, this big program to build a space shuttle, as we'll be able to have, we'll be able to colonize the moon, and we'll reduce the cost of a pound in space from $20,000 to $1,000. That was their goal, was $1,000 a pound if you go back and look at the 1970s type of data. But it wouldn't have gotten through Congress if it didn't have the support of the Defense Department. Okay, it turns out the Space Shuttle main cargo bay just happens to be the same size as a space-based laser weapon. Okay, just a coincidence. Okay, and if it weren't for the fact that the Defense Department was cheering on NASA and the committees in Congress, they wouldn't have gotten it approved because you couldn't justify it on just purely commercial reasons. Anyway, the fuel for this reusable space plane was supposed to be H2O. H, 2 hydrogen tanks and 1 oxygen tank, H2O, okay? And they were going to save further weight because they were going to integrate, the tanks were going to be part of the structural strength of the whole system. So this was just the skin on the outside that was going to deflect the hot gases and things like that. This was an aluminum tank. These were supposed to be composites for hydrogen, and this was going to go all the way from Edwards it was going to go from Edwards to Dugway Proving Grounds in Utah. That was its flight. I can't remember where it started and where it ended. It was either vice versa, one or the other. It was supposed to get up to 100 miles in space and land, and essentially had wheels on it, okay? It was supposed to land. Well, they built it. In fact, they built it, and I was there, I got to go there, in the same hangar where they built the stealth fighter at Edwards Air Force Base, okay? So this was a super secret hangar at Edwards. And the problem was, when they were building this thing, well, they had it, after the first Gulf War, the Defense Department decided they should go for rapid prototyping. That was a big thing 25 years ago. Because, you won't remember, but we held off the war for 6 months while we mobilized, okay, in Saudi Arabia. And remember, the Hussein had taken over Kuwait, and we announced we were going to invade Iraq and take back Kuwait and stuff, and the Saudis were in favor of all of this. And so we took 6 months to move everything over there by ship and everything else. The second Gulf War, it didn't take that long. We basically announced we were going to go to war, and we were at war within a week. And, the first Gulf War lasted like 3 days, okay, because we took 6 months to prepare for it. You don't always get to prepare for war like that. But in any case, the Defense Department decided They needed to rapidly prototype things because they were not ready in 1990 for a desert war. Okay? For example, the helicopters in the desert with all the sand, the engines would last 30 minutes. All that sand would go through the engines and whoosh, you'd abrade away your engines. Okay? Engines only lasted 30 minutes. They had to solve problems like that. So they decided to make this a rapid prototyping project. It was 33 months maybe, I don't remember, from lead of contract to first flight. Okay? They had to design it and build it. They tried to design it out of rib-stiffened, three-dimensional woven composites, and that was what they bid on. And then they actually got the contract. This is Lockheed Martin, Skunk Works in Edwards Air Force Base. And then they went out to price this. And they found out, oh, composites are expensive. Okay? In fact, they were going to blow their whole budget on these 3D woven composites. Plus, it was going to take a while. You know how you make 3D woven composites? You have someone with a needle and thread. Okay? Literally. Okay? Running the carbon fibers in a third dimension. You know, no wonder it was expensive. Anyway, so they decided they only had 2 months left of their 6-month budget for the design phase. So they came up with this, which was the Nomex honeycomb core, which you could buy off the shelf, not at Home Depot, but you could buy it from the companies that made it. It was off-the-shelf product. And the graphite fiber laminate tape, cloth you could buy, and you could buy the resin, and they just happened to have a big autoclave at Morton Thiokol plant in northern Utah, up near Logan, Utah, and they looked on the website, and 3M was selling this adhesive that they could glue the whole thing together in the autoclave. And they looked at the data sheet for the 3M adhesive, which you had to keep in a refrigerator. It said it had a shelf life of 10 days outside of the refrigerator. They decided they could lay everything up and get it into the autoclave within 10 days. What they didn't say was that the strength was only 10% of the original adhesive strength after 10 days. Okay? They were figuring it would have 80-90% of its strength, not 10% of its strength. So they put it into the autoclave, and they needed four little lobes of each one. They put them in the autoclave, and they were going to join each those four lobes together to make 2 tanks. They made 10 just in case. They knew they might have some problems. They came out, and some of them had delaminated in the autoclave. One of the problems with the composites, there's no way to repair it. Okay? If you don't get it right the first time, it's junk. Well, they had about 7 of them that were pretty good. So the 8th, they decided, well, it might be okay. And they had a design safety factor of 2. Only with the delaminations, it wasn't quite 2 anymore. So they sharpened their pencils, and they really sharpened their pencils. And they had a design safety of 1.05. Okay? Well, 1.05 is greater than 1, so therefore it's good, right? Good to go. After all, we got a $1.3 billion contract here, and we don't want to go and tell them that, we have a 33-month deadline and blah, blah, blah. So let's put it in test. Where do you put it in test where you can get 5,000 gallons of liquid hydrogen? Well, you just go down to your local, no, you can't. You have to go to Huntsville, Alabama, and NASA has, where are you from? Okay, and what do they have in Huntsville? A big facility. Well, NASA and the Army both have a facility, but this was actually at the NASA facility, but the two are sort of joined at the hip. They're, Redstone Arsenal, and anyway, and I got to go there, okay, and see this tank of liquid hydrogen. And then one of these tanks got to go there, and it got to be filled up with liquid hydrogen, and they were sort of sweating their 1.05 safety factor. They fill it up with liquid hydrogen. The whole thing doesn't spring a leak, and they're starting to cool it or warm it up, and they're giving each other high fives, and they're on the video camera because you don't let anyone right in the place with the 5,000 gallons of liquid hydrogen that might leak and go boom. You giving each other high fives, and on the video camera they see this burst, and they have a leak. okay? And it turns out hydrogen got inside the pores, liquid hydrogen got inside the pores as it warmed up. All of a sudden it built up pressure and it blew up, and they canceled the $1.3 billion program, okay? So we did not for a while have a replacement for the space shuttle. In fact, now we have SpaceX and other things, but this program got canceled. But this was $12,000 a pound fabricated, okay? It was the size, each one of these tanks was about the size of a two-story house and stuff. But it was all part of structural frame design. They had Inconel little struts holding things together. That's what these things are. These little triangular frame things are Inconel struts holding everything together. And everything else just a skin on the outside for aerodynamics. Another material from aerospace, I said this before, the first large-scale production of carbon fiber aircraft was the V22 Osprey, which is tilt-rotor helicopter. Bell had invented tilt rotors back in the 1960s. They built a couple of prototypes for NASA. And basically, the advantage of a tilt rotor, does anybody know the advantage of a tilt rotor versus a fixed wing or a helicopter? It's actually a hybrid of both. And the whole nacelle, that nacelle is large enough for a person to walk in. I walked into the nacelle of Ship 4, okay? I could stand up, okay? Carbon fiber has to be lightweight because these are big, powerful engines. But when you're in helicopter mode, you need a big, powerful engine. When you're in regular airplane flight mode, you don't have to have such a powerful engine. But in any case, when you're going to go into helicopter mode, you need a lot of power, and the engines were tied together with carbon fiber composite tubes, torque tubes. And anyway, they had Ship 1 was just a prototype mock-up so you could walk in it. It never flew. It wasn't designed to fly. I'm not sure it ever had engines in it. It was just to see if things would fit together, okay? Ship 2 was at Philadelphia, Boeing Vertol plant in Philadelphia, and they had taken it up about 10 or 12 feet in the ground, off the ground, and this is all on video. It's sort of an interesting video. I'm sure you'll probably find it on YouTube now. But anyway, and so it's hovering there in a helicopter mode, and then all of a sudden you see it start to oscillate a little bit, and then it goes flip, it flips on its back and destroyed itself. What had happened was they had a test pilot, and they all walked away. But someone had miswired the controls, okay? It had two wires, so that if the pilot put in the input to go right or left, it would supposed to go right or left. Well, when they flipped the wires, it would go left when you said right, and vice versa. And so what happened is he was trying to stabilize the thing. He just made the oscillations bigger until whoosh, he flipped it over like a turtle. And that was sort of an embarrassment. And then Ship 4 was the one that I worked on. It had crashed at Pawtuxet, Maryland, and a number of people died. And it was a problem. They had a fire in the nacelle, okay? And the question, did the fire start in the engine in the bottom or the gearbox in the top? The Navy determined that it was a fire in the engine in the bottom. They had 400 findings of facts. I disputed it. And after went to trial, and I testified, and afterwards the Judge Advocate General Corps of the Navy went back and looked at the Navy's 400 findings of facts and reversed it to what I said happened. They had a hydraulic leak up here, okay? And they had a big fire when the hydraulics let go. That's a longer story. Anyway, it does fly. It's supposed to cost like $6 million. It ended up costing $40 to $60 million. But it flies, and it was a V22 Osprey that was the first aircraft in when they captured Osama bin Laden. Why? Because they're quiet. Helicopters are noisy. Airplane mode is nice and quiet. okay? And they can go 300 miles range and stuff on these things. Anybody know why the helicopters can't go, why they're so noisy and why they can't go faster? I mean, this thing can go 300 miles an hour and a 300-mile range or something, whereas helicopters can't go more than about 200 miles an hour. Anybody know why? It has to do with the rotor blades. Turns out if you're going in that direction, the rotor blades are going around like this, there's no problem for the rotor blade that's retarding, but the one that's going forward is sweeping around, and when it reaches sonic velocity, all of a sudden you get vibrations and noise and everything else. And so you can't exceed the speed of sound on a helicopter blade without having tremendous energy. NASA did it, and if you go to Langley, you'll see a test helicopter where they actually did go faster with the tip speed above the speed of sound, but only for a few seconds. Okay. So there's carbon fiber. You couldn't have built this aircraft without it. We actually have gotten carbon fiber. Anybody know anything about the BMW i3? So how could you afford carbon fiber composites that might cost you $50 a pound fabricated when you can only put $2 a pound into the vehicle? Well, first of all, it's not a $20,000 vehicle. It's a $60,000 vehicle if you start pricing it out. Second of all, they basically decided to build it in the state of Washington next to hydroelectric plants because one of the big costs of the carbon fiber is the energy to take this stuff and turn it into carbon fiber. You have to heat it up to 2,000 degrees centigrade and stuff to make the carbon fiber composites. And they basically built it where energy was cheap. Okay, they moved to the price of cheap energy. And the other thing, I haven't looked at one. There were a number of things they did that were very, very innovative on the part of BMW to get the price down. One of my former students bought a BMW i7, which is the big $100,000 sports car, $140,000 less, but Chris tells me they deep discount them. He got his for $100. And he did his thesis on polymers, and his comment was, the carbon fiber composites are junk. Okay, I mean they're not made well. They're fine for just a shell on the outside of the vehicle. Okay, and it's lightweight, but the quality of the resin transfer molding would never pass the aerospace industry. Okay, so low quality, high cost material, but they've innovated and they've made a couple of vehicles, first ones in the world. And 20 years ago, no one ever thought they could do it. But it's been done. Okay? Some things, like ships, need very little energy to move. All you got to do is slide them through the water. And so that's how you get down to low enough material cost. Some things, you don't care about density. Like this is a big pressure vessel. And they're actually just transporting one half of it. The rest of it's a great big reactor for a refinery, and this is just the front of it when they're transporting it, and you can see all the wheels and stuff here. Large vessels don't usually move, so we don't care if we make them out of something heavy like steel. Okay, so speed versus cost, there's lots of different price points depending on what you're doing. So now we're going to change topics. Anybody have any questions on, or any examples of your own on price points of speed versus cost? And this $2 a pound for an automobile can have a wide range depending on where your actual application is. If we get back to the science of material properties, we're finished up on, we did externalities and we did cost and availability, and now we want to talk about material properties. There are limits to the properties of materials, and some people will design systems that are way beyond whatever we can really do. Did I tell you about the Air Force propulsion program? And they wanted to, this was a committee I was on down in Washington about 12 years ago, And the Air Force had a couple of requirements. One is they wanted to have an engine that could go Mach 17. Well, Mach 17 is, basically the speed of the satellites going around the Earth, right? 15,000 miles an hour or something like that. And I said, in air? And they said, yes. I said, this is human powered, man-rated. And they said, no, it's not. And I said, why do you need something that will go Mach 17 in air? Because if you look at the frictional heating of the skin, you get to temperatures of 6,000 or 7,000 Kelvin. And now we're only talking about 3 or 4 materials in the world. Carbon, hafnium carbide. I mean, there's only 3 or 4 materials that don't melt or vaporize at 6,000 Kelvin, okay? And so you have a very limited choice of materials. Now, they said, well, we can use things like active cooling. That was what they had proposed for the National Aerospace Plane back in the mid-'80s. Well, the National Aerospace Plane was going to be hydrogen fueled, and they were going to make it out of the skin out of copper because it had great thermal conductivity, and they were going to pump the liquid hydrogen through the skin, and the copper was going to be 1 or 2 millimeters thick. And so you'd have, on one side, you'd have 4,000 or 5,000 degrees Kelvin, and on the other side, you'd have liquid hydrogen at 20 degrees Kelvin. And as long as you didn't have a leak, everything was fine. But if you ever had a leak, you have a big bomb. So it wasn't a great design. But that's what the Air Force wanted to do. And I said, why do you need Mach 17 in air? And they said, this is like 2003, 2004, 2005 time frame. They said, well, once we knew where Osama bin Laden was, but we had to get ordnance on site within 15 minutes. And we didn't have anything fast enough to get there. Okay, we couldn't fly helicopters in there in 15 minutes. We couldn't get a cruise missile in from an aircraft carrier in the Gulf within that time frame. And we couldn't get him, okay? But they knew where he was, but he was going to be gone in 15 minutes. Well, so he got away that time. So they want something that'll go Mach 17, and they would have been able to launch it off an aircraft carrier in the Gulf, and they could have gotten the ordnance in there and blown them up. Okay, well, that was one thing they wanted to do. The other thing they wanted to do is they wanted to have an aircraft that would fly 25,000 miles without refueling. And I said, excuse me? The Earth is only 25,000 miles in circumference, and so you should only need something you can get to any place in the world with a 12,000-mile flight. Okay. In fact, last summer, not this summer, but the summer before last, I took the longest flight in the world, 17 hours, Dallas to Sydney, 17 hours on one airplane, the Airbus A380. It's a long flight, but you can get there, and that's about 12,000 miles. And there's never going to be a longer flight than that because you go a great circle. Well, they said, we figure that in the future we will not have any air bases except in the continental United States. We can't expect to have air bases. They didn't say it, but the Filipinos are going to kick us out. And, the Japanese are going to kick us out of Okinawa. You name it. We won't be able to use Diego Garcia or whatever. And so they wanted to have an air. Oh, great, okay. Well, the requirements to have these types of things for lightweight materials are horrendous, okay? But that's what people will design when they have no constraints. They'll say that's what they'd like to have. But we do have constraints, and it's the strength of the chemical bond. So this is what's originally was called the Leonard-Jones potential in the 1920s. It came out of quantum mechanics and the Bohr atom and stuff. And basically, this is the energy of a bond versus spacing between the atoms. So if I got one atom here and I got another atom, and I bring it closer and closer, there'll be a minimum energy of separation. X is the intermolecular separation between the atoms and the crystal. As you heat things up, at lower temperatures, you'll have a certain vibrational energy. And at higher temperatures with more thermal energy, you'll have greater vibration, and that leads to thermal expansion, okay? Higher thermal expansion at higher temperatures and higher vibrations. And if we look at thermal expansion, we find that some of the polymers have very large thermal expansion. This is a log scale, folks. Then you got some metals, then you got some ceramics. Diamond has the lowest coefficient of thermal expansion of 10 to the minus 6 per degree Kelvin. Okay. If you look at Young's modulus, it goes the opposite direction. Diamond has the highest Young's modulus. Metals are down here, order of magnitude lower, and the polymers are another order of magnitude down. So we're limited by the strength of the chemical bonds, and if we look at the strength of chemical bonds, we've got different bond lengths. So we got primary bonds, covalent, metallic, ionic. You should have learned this in freshman chemistry if you were an MIT student. And they have these bond lengths. You can also talk about the bond energy in kilojoules per mole. I learned it in electron volts. The main primary bonds are typically 1 to 3 electron volts. Metallic bonds have a larger range. They go over several atomic distances. I mean, that's 5 angstroms. That's more than 1 atom distance. 5 angstroms. The secondary bonding, van der Waals and hydrogen bonds, are an order of magnitude or 2 orders of magnitude lower, so far as that goes. And so that determines the properties of things. Polymers are low temperature materials because they're not held together in a 3-dimensional structure with covalent or primary bonds. They're held together with van der Waals bonds. Along the length where the primary bonds are, tremendous strength. That's Kevlar and stuff. The fibers can be very strong because you got primary bonds along the fiber, but you got secondary bonds between the fibers, and therefore polymers are low temperature materials. The strongest material in the world is diamond because it's a 3-dimensional structure of covalent bonds. So everything relates back to the bonds. We can look at this. In thermodynamics, there's Richard's rule and Troughton's rule. Basically, if you look at the enthalpy of melting or boiling and you find the transition temperature, Richard's rule and Troughton's rule is basically just the energy necessary to break all the bonds. Break 10% of the bonds for melting and break all of the bonds, 100% of the bonds for boiling. And there's a very good relationship between the strength of the bond, the temperature, melting point, and all those things. If we look at the properties that are limited by bonding, yes, it's true that diamond is 1,000 gigapascals, but most materials like molybdenum, carbon fibers are about 60,000 KSI, 400 gigapascals. Steel is half of this, which is actually very high and good, but it's nowhere near the few materials like molybdenum, tungsten, and carbon fibers that are double steel. Melting temperature, tungsten's got the highest melting temperature, just like it has one of the highest moduli, because it's the strength of that chemical bond. Toughness. What is toughness? Toughness is the ability to absorb energy. Something that is, in the science of fracture mechanics, something that is brittle will be very sensitive to flaws and defects. I can take a piece of paper, see me doing this on the History Channel, and you can pull on it with several pounds of force. If you put a notch in it, a flaw, instead of pounds, it takes ounces. You can lose 80 to 90% of your strength because of the flaws in the material. A number one of Bob Sprague's comments was, physicists think that structure controls properties of materials. Metallurgists know that defects control the properties of materials. It's the defects in the material, and we'll talk about that later as well, as far as that goes. If you have a tough material, rubber is a tough material, put a great big notch in this, and I can pull on it, and all it does is blunt, and I no longer have a sharp notch. So rubber is a tough material, paper is a brittle material. You can tell a brittle material, if you break it and you try to put it back together, it matches. You take a ductile material and you break it, and Brian will bring in some samples tomorrow that'll show a ductile material. You can't put it back together in the same shape because everything's stretched and deformed. The highest toughness in the world is some of the superalloy metals, around 300 megapascal square root a meter. Unusual units, we'll get to that. The cost can go from gravel, stone, to unlimited. People pay tremendous prices for some materials. Ductility, a good material would be 30%. A brittle material can be essentially 0.1%, up to 1,000% for some superplastic materials. Generally, these things vary over about a factor of 100,000, not just on the chemical bonds, but on other things as well, and we'll talk about those. So Brian will lecture tomorrow. Simone will be here on Thursday. Friday's off, and I'll be here all of next week. And Dr. Belmar will be back after that.